So this is the tool which we have developed. There are 8 models, and there will be a data which is provided by NASA, that is called as a CMAPSS. That means it stands for Commercial Modular Aero Propulsion System Simulation. It is a system developed by NASA to study engine degradation. Now the engine we're going to analyze is the one is called as a turbofan engine, and this is the design of a turbofan engine. This is low pressure compressor, this is high pressure compressor, this is high pressure turbine, this is low pressure turbine, this is a nozzle, and this is a fan combustor. And we'll look at the data which will be used by us, and this important components as we mentioned here. During operations, degradation occurs in each of these components. If the degradation level of if any of the components exceeds a threshold, the engine is said to be have failed. We don't want a jet engine to fail in mid-air. Therefore, jet engines are inspected before every takeoff. Now, there are training the data which is comprised of this particular files, and these are the train data, then there is a test data, and the remaining useful life data is there. Now if you look at the application which we have developed here, we got to load the data for the train data. So there are different different sets like FD001, FD002, FD003 and FD004 for train, test and remaining useful life, that is RUL data. So we will be inputting we'll be fetching the data from here, like we just got to click here, load, and it will go to the folder where this data is. This is CMAPSS data. This is provided by NASA, and then we'll for this particular this particular module will use the FD001. That is first we got to enter is the train data, FD001.txt. Then the test data, will take the test data from here, and that's test FD001, and then we'll have the RUL data of FD001. So this is the data we put. We are going to try explanatory data analysis and baseline. This is a regression model, and the output path we'll have to give. I have just created an output folder which is blank, and the data once the processing is done, the folder will be for this particular baseline model, it will be stored here. So we just open this and direct the output folder. So here the data will be there, and these are the 8 modules we are experimenting for this particular predictive maintenance, and which will give us the total analysis which model or which algorithms gives the best result. For that we need to first understand how it works, and I have segregated, I've already run this particular application, and all the data is actually stored here, output is stored here, because it takes time to generate this data, because there are a lot of graphs So whatever we can within this demo period, whatever we can generate, it will be generated, the output will be generated in this folder. So the other part of it is understanding the data, and now that we have seen this is what we are trying to analyze or predict, basically, that what would be the time of failure for a particular engine. So first we'll look at the data. This is readme file is there, provided by NASA. So we'll look into this FD001, which we input right now over here. This particular FD001, throughout we have used for train, test and RUL data. We were using FD001. So what are the features about that? This particular set contains of 100 engines. These are the train data set. This is the test data set, which contains 100 engines. Operating condition is 1 at the sea level, and the fault mode is 1, that is high pressure compressor degradation. So this we got to run this particular data, and based on that, what does the training set data contain then, basically. So we'll just have a look first on the training set data of FD001. So here it is, and this is the way it is, the data provided by NASA, which is real-time data, and the training set contains the number of engines being run simultaneously until it fails. That is, for each engine data were collected to the point it failed. So first engine, this is engine, okay, we'll go and check the other part of it to make it more understanding and more clarity about that. Then there is a test data. This test data FD001, we'll just open this. So this what does it contain is it's slightly different because it is available for arbitrary number of cycles. What does cycle mean? Cycle means engine starts, it takes off, it lands, and engine stops. That is one cycle. So this is first column is engine number 1, and the cycle means how many times it flew, basically. Engine started till the engine stop event happened. So if you look at it, if you go down, we'll get this thing much more clearer later on. So this is the test data, and the RUL data is the remaining useful life of that particular engine. Particular engine is this much. For FD001 is 112, which I'll explain it later on when it comes to the to make it more precise and clearer. So this is the RUL data. What it does is the task is to predict how many cycles after each engine will fail. This predicted value is our remaining useful life. So our goal is to predict the remaining useful life of the engine as accurately as possible from the operational data. This was the operational data which we are looking at, it provided by NASA, and that's why we call this data as a data-driven remaining useful life prediction. So we'll look at the data set basically now. I'll close this files because it will keep on increasing once I open it. So what we'll do is go to this particular data. So this is the folder which we had looked on, and we just saw the FD001. So this is the data format. What fields are there? Basically the index is the first field, and then the ID. This is the engine ID, that is engine 1, 2, 3, 4, that way. And then the cycle, as I said, how many cycles that engine has run from engine start, takeoff, landing to engine stop. So settings, there are the operational settings for this can be seen here. We just about to open that README file provided by NASA. So we'll just so this is the condition 1 at sea level. Now FD002 has got 260 engines in train set and 259 in the test trajectories, and the fault mode is 1, that is high pressure compression degradation. And then there's a data set FD003 which is having 100 engines and 1 country operational condition and 2 fault modes, that is high pressure compressor degradation and fan degradation, as we saw here in the this fan degradation and the high pressure compressor degradation. So these are the fault modes in FD003, and FD004 has 248 engines and test trajectories have test data has got 249, one more, and that's that's the way it's getting it's calculated, and the conditions are 6. Here also in FD200 there are 6 operating conditions, and the fault modes are HPC, means high pressure compressor degradation and fan degradation. So these are the basic data features we have provided by NASA. And now that we'll look at this particular data format. So setting, then these are sensors S1, S2. There are 21 sensors used for measuring the signal, for measuring sensor measurement, that's the signals, and these are the columns which we saw in that particular FD001 TXT. And now then we'll have these are the sample training data, I mean to say what we are working on right now, what we have uploaded and what we're going to use it. For the training data, there will be approximately, that's FD001, this is 20,000 rows are there, 100 unique engine IDs are there. And this is the ID, this is engine 1. This is the cycle 1, 2, 3. So the cycle, once it reaches 192, the remaining, means here the engine failed. So here the remaining useful life becomes 0. From start, if you look at it, the remaining life of this first engine is 192, and then it will degrade to 0, remaining useful life. And these are the settings, 3 settings out there, and these are the 21 sensors, measurements, the signals. And this is the testing data, which has got 30,000 rows and 100 unique engine IDs are there. And here also, if you look if you look on the training data, you can see the second engine flew for how many cycles? For 286 cycles, and that means engine start, takeoff, landing, and then engine stop. 286 times it flew, and then 287 times, and then it engine failed. So this is the way the data is given, and then the setting operations. Now we'll look at the test data. We'll have this is engine 1 in the test data, and the cycles which are there. Here it is incomplete in the testing data. The testing data, engine 1 has only 31 cycles, but if you look at it, there will be this is incomplete, where the event has not occurred, that is the engine failure has not occurred. So it is 31, and then we'll get the data from the ground truth data, that is RUL, that is a remaining useful life file. That is for first engine it is 31 year, and here it is 112, the first engine. So you got to add 31 plus 112, whatever the figure is, the number of cycles it flew. It was after that the engine failed. So 31 plus 112, whatever the figure is, the is the number of cycles this particular engine one flew, and then it failed. The same way with test data, it is incomplete. The event has not occurred, that is the engine failure. That much only data is provided is for 49 cycles for engine 2. And if you look at 98, that is the second engine, then add 49 plus 98. That would be the number of cycles after that the engine failed. And similarly on the third engine in the test data, it flew here 126 cycles, and here it is 69. So 126 plus 69 is the number of cycles it flew, and then the engine failed. So this is the way it is. These are the sensor measurements, S1, S2 sensor, till there are 21 sensors, and the operational settings as we just looked into it. These are the settings 1, 2 and 3. So this data has been provided by NASA, and based on this we are experimenting with the different algorithms, different models within the machine learning. This is called as a supervised machine learning, and we'll see which model gives us the best possible remaining useful life with a minimized errors, minimizing the errors, what we can predict that when the engine will fail. So this is and then this is the same thing what we saw. This is unit number, that is the engine number of cycles, settings 1, setting 2 and setting 3. I meant to say, and then the sensors till 21. And then this is FD001, what we have right now input for the first model to execute. Here is FD001, and the train, then the train test and the RUL data. So okay, and I think that's it for this data type. Close this. Okay, so we got a basic idea of what we are trying to do. So let's see this algorithm. This is a regression algorithm, linear regression algorithm, and what output does it give? We'll see in the output folder, which is here. One second, we just close this. This is the design of the turbofan jet engine, which we are trying to analyze. And we will just close this folder also, this also, and this is the output folder, which is blank. We'll see that the output is delivered here. We just got to click on this. Do you want to continue? Say yes. So now the processing will start. So load data initialization. So the processing has started. There are few models which will take a lot of time to give the output, so I've just already used this application, and the output has already been stored in the engine folder. which I showed you earlier. We will use that because I don't think so we will be able to complete before it takes a lot of time for graphs to get generated. So we'll just go to the engine folder and see, and I have segregated the data in such a way that it is more explanatory. So this is the way it is processing, and it takes time to process. By the time I can just show the it's done. So this process is terminated successfully. We'll go to the folder, output folder, which was blank. The folder has been generated, and this is the results been shown here. So this is evaluate, what we are doing evaluation, and we'll look at what the evaluation is all about. So the most important criteria matrix we're going to look at is the RMSE, this one, because what we are looking at is the root mean square error indicates how many cycles the predictions are off average. So this is the difference between what is the difference between the real data and the predicted data. To minimize that errors, this particular figure has to be taken into consideration. So to minimize error of the real values and the predicted values. So here it is 31.95. We'll keep this as a baseline matrix, and look for the other models how well they perform. This has to be as minimum as possible. This is 31.95 is not the right metrics actually. So this is one. Then what was generated was this is remaining useful life graph. So this is the graph where you can see this is sensor 12, and this is the declining regression. This is declining regression, linear regression. So if you can see the sensors initially, if you look at it, these are the when the engine when engine is first used. It fluctuates a lot, and it is not in line with the regression, linear regression. As the wear and tear of the engine happens, these are the signals of sensor 12. It starts correlating with the linear declining linear degradation model. So these are the signals, the measurements you can say of sensors, and these are the remaining useful life once the engine starts. So if you look at it, this particular thing has to go to 0 when the engine fails, and this is the remaining useful life. So its degradation is happening as the engine is being used over the time. So this is one. We'll see the other one. What's been generated is the frequency of the remaining useful life of taking into consideration all the engines, 100 engines. Hundred engines we are using in that data set of FD001. So most of the engines fail after 200 cycles. These are the cycles, basically remaining useful life. After 200 cycles, after 200 times it flew over the period, it starts, it encounters the failure, engine failure, maybe of high pressure compressor degradation. We are taking one for this particular data set. So that happens mostly after 200 cycles. So this is the way we are analyzing this data set. Then these are the sensors and its sensor values. this is pretty flat, and this gives no information basically. This is sensor 1, and you can see sensor 2, and so on and so forth. Just give you a brief of this, how it is done. So this is going on upward trend. So what I have done is basically, rather than going through this to make you understand in a much what do you say, 1 second, the much precise manner, much more clarity, I have segregated this particular folders. For the first one is the baseline, and all the data is there. I'll give more information on this particular output rather than taking it from the model. That is more of a technical part, and this would be more understanding to a non-technical person also. So first thing what we saw was the RMSE, that is the root mean squared matrix, and that is 31.95. we keep a check on that. Let's keep them as a baseline matrix. Then this is something we got to if you understand, it's you get more clarity about what's happening. So just check, we can put the other one also. Now that we have loaded, means we have come with the output of ED and baseline. Let's look at the second model, that is updated assumptions of remaining useful life, and that is second one is a support vector regression. That with this we got to just click on the update RU assumption, and for the model the app didn't require the time. Okay, degradation model, fine. So that's not a problem. So we just click on the second one with the same data set, FD001, with the same output folder, and we just close that folder, I guess. We'll close this folder, and we'll close this, and we were having a look of the folder which I have just sorted out for a better understanding. For this we just got to, same way, we just got to click on this, and do you want to continue? Yes. So it will start processing this. It will take some time to generate the output. So we just going to keep it down and minimize it, and we'll go to this particular folder of the first one which we went. So here if you have a look, we'll have a graphical interpretation of all the outputs. So here if you look at it, this is first engine, the number of cycles. The remaining useful life, that column says it is 191 remaining useful life cycles is there, then 190, 189. When it reaches this particular figure, this particular column reaches 0, that is where the engine broke, and that will come when the cycle numbers will be 192. 192 on cycle 192, the remaining useful life of that particular engine becomes 0 for the engine number 1, and this is the way it works. So, and we can see from the first from the data set, we can see is here. We can just we just can go to this particular data, that is test. We'll go to train data FD001, open it, and if you look at the first cycle, it goes to 192. This is, yeah, the first cycle ends at 192. First engine has a number of cycles that it flew was 192. Then the second engine starts, and so on and so forth. So it's 192. So what is the point here is when it reaches 192, this particular column, this particular column, which is that is number of cycles, which is 192, the remaining useful life will be 0, and this is the way it's been predicted. So now we can we'll have a look on to other graphs. This is as I said, we saw earlier when the output was generated, this particular engines normally fail based on this data. This fails at around 200 cycles, most of the engines. So the rest of the engines fail accordingly this particular number of cycles, and it goes to 362. I think this particular there are engines which flew 360 plus cycles, and then it failed. So this is the way to understand the distribution. And then we have this particular operational condition settings, setting 1, setting 2, setting 3. So if you look at it, there is a mean, standard deviation, mean and minimum 25%, 50, 75%, and maximum. So here if you look at it, the standard deviation is not too much between the settings 1 and setting is almost negligible. So the operating conditions, basically here it is all 100%. So the operating conditions, there is no difference between the operating conditions, there is a minimal difference. So it's quite stable between basically settings 1, setting 2 and setting 3. Then this is where what we saw the earlier also in that output was this is the degradation model, linear regression degradation model from the start of the cycles. The sensor 12 we are looking at, and what it gives the measurements, and then it degrades, the linear model comes, and it starts degrading to 0. So remaining useful life becomes 0 till then. These are the fluctuations of the signals of the sensor 12, and then this is a unit. Okay, this says in FD001 data set, in the training set there are 100 engines. One minimum is 1, maximum is 100, and the standard deviation is 29. That's okay. And here it shows the number of cycles. So the first cycle in the test training data, what we saw, the first engine that failed broke down was at 120. After 128 cycles it broke down, and the maximum, as we showed earlier on that distribution graph, 360 cycles were flown for a particular engine. So there is a minimum first breakdown of the engine happened in this data set at 128 cycles, and the maximum it went to 362 cycles. So the standard deviation is 46. That is a bit too much basically, and you got to work on this particular area. So this is the way this particular stats are. And then this is also, here you can see the sensors which are not in the standard deviation column, you can see, and this particular this particular minimum to maximum to you can see there's no change in the signals basically. So this are irrelevant data. This one S1, then this is plus 0. So we go down. We can look at this also. 18 and 19 sensor number, they are useless. 388 because they don't derive any information. It's just a constant. It's a flat line. So 3888 and here also 100, and then there is one more 5. You can see here also the data sensor 5. You can see the data is constant. Doesn't give any basically information. So 7 sensor 5 and sensor 16 also is something like this here, 300, and these are not does not provide any information. So this should be neglected when this sensor should not be used while analyzing and evaluating the predicted useful life of remaining life of the particular engine. So this is the way, and then we'll just have a look at what was there. Yeah, so we just went through this part of it. Now the signals of the sensors, as I said, there are 21 sensors. Out of this is a declining trend. So we just open it, and this is the declining trend of this particular we are talking about. Of this, basically these are the sensors and the signals which are declining. This needs to be taken into consideration when evaluating and analyzing of that particular engine. So this is declining, okay, and declining trend. Then there is a flat line, as I spoke. These are useless because it will just generate a flat line with no information, useful information to be used to analyze. And these are the sensors 16, 18, 19, these are the sensor 19. So this has no consideration. And then we'll have a highest fluctuations. These are the ones which fluctuate the most, sensor 9 and sensor 14. See, you can see these fluctuations. This is a noise basically of the signals, sensor measurements, the noise it is making, and this needs to be taken into consideration for analyzing. Sensor 14 also is having the same sort of noise. Then we'll have peak downwards, and you can see downwards it will have this is downwards going downward. This also needs to be taken into consideration. This is sensor 6, but somehow somewhere down the line it doesn't give much information but can be tested. Then there is a rising trend. This is a rising of the sensors which are the signals on the rise. This is rising, all rising. This has to be taken into consideration for the analysis. So this is the way I have segregated the data, and I have segregated data for all the modules, that is all the 8 modules. You can see it here. I won't be able to show the whole because it's going to take a lot of time generating the data and then explaining that. So this we saw, this one we saw right now, and then the second one which is generating at the moment, we'll see that also. So this we'll see as soon as the output is generated, and this too we will see. Otherwise the rest which I have segregated is then we've got the time series. There are a lot of data in that also to be explained. Time series is there, then survival analysis. This is survival analysis, and this is random forest. This will use a different data set. This will use the data set of FD003. so which will have the different remaining useful life for training, test, and RUL data. This is reproducible results premier. This module also is there, and then lagged MLP. This is which contains a lot of output, and then the last one is long short-term memory model. That's all algorithms which will use FD004, the data set, which has got two fault modes, that is fan and compressor, high pressure compressor. So this will be used for, and here in lagged MLP FD002, which also has got two fault modes, which will be looked into it. Like it's the same, the fan degradation and the compressor, high pressure compressor degradation. Oh yeah, we have just processed the second one. The same way it can be taken for the rest of the thing: time series, survival analysis, random forest, reproducible, as we saw this particular folders which I showed, and the output is generated, and then you can evaluate with the RMSB, that is root mean square error, and whatever the minimum is there. We're going to see the most, as I've already run this particular, all this algorithms models. So the best one is, we'll just see the output here in the output folder. So yeah, the updated RUL and SVR. This is the best possible solution of all which we have analyzed and experimented with, and this would reflect basically the output of the application. So we'll just have a look and evaluate. Okay, this is where it is 20.54 is the 24.54 is the best possible matrix we have achieved after running all the different models, and this is the optimal we can say for this particular data set. And the way I just go here, 1 second, I'll just close this. The updated this is what I have basically created the folder for this particular model, and which shows the same thing. And here I just want to showcase this is what is the best possible solution. Here this is called as a clipped RUL. This you can see at this is also called as an early RUL. This is also called as an piecewise degradation model. This is linear degradation model, linear regression degradation model, and the piecewise. Here what it is done is on the early RUL, that is when the engine when the cycle starts, when the engine initially the engines are excuse me, when initially the engines have started been used, there is not much of wear and tear on the engines. So the signals which you see of the particular sensors are much more constant within this particular area till 125 say 1.25 cycles. For that is the engine start, takeoff, landing, and engine stop. 125 times is done. We just taken that particular figure. So after 125 cycles, it starts degrading, and this is the linear regression degrading model. This is the piecewise degradation model, and this performs the best. This is the clipped, as you see. This has been clipped till 125 cycles, clipped RUL in green, and then the RUL that is in black, that is this it goes to 0, and this is sensor 12. So this is the best possible root mean error. I meant to say, this is what the evaluation, when it's been evaluated, this is by far the best possible matrix derived. When we run all the 8 models, this is the best. So this particular model is optimal, 20.54, the minimized. This is the minimized error between real and predicted value, and this is support vector that differs from regression by setting boundaries at the distance. This is what basically setting a boundaries at the distant epsilon. Before that, I just show you this. This is basically called as a SVR epsilon. So this is the target. This is the target. This is the target variable, that is the remaining useful life. This is a linear model. Basically, you can look at it that way. And this is the boundaries. These boundaries are the distance between the target variable and the boundaries is called as an epsilon. And these are the data points which has to be within this particular boundaries. Now, if you look at this, this is what the support vector regression is. It fits into basically it fits the basic model in this particular way. This is the linear model we are talking about. That's what we saw earlier, the target variable, and then the RBF, that is rapid basis model, and rapid basis function model, and this is the polynomial model. If you look at the polynomial model, this is blue. It goes here, it connects all the data points, and it comes here. And within RBF model, you can just see this is these are all connected data points, and basically this is what it is called as a support vector regression, and that this black is all data points. So this is what is all about this particular updated RUL and support vector. And this is the epsilon, the distance between what we saw here, the distance, this is the distance. So distance between, I will show, yeah, the distance is 0.4, the RMS is that is root mean square error is 19, and the best works is the 0.2, which is 19.74. So this is by far the most optimal solution we derived after using all the different algorithms. And basically, if you look at it, you can always have a you can always look into it, like what basically should be done to predict basically the maintenance of a aircraft engine. So you should be able to calculate and predict the health index, key performance indicators informing an overall. There should be a key performance KPIs for informing an overall health of the equipment, each sensor's contribution to overall score, complex pre-processing and neural network architecture, running more iteration, and also tuning the optimizer, and learning rate could probably push this further. So this is the way this particular application was developed, basically doing the experiments, and the airline can choose one of the models which they think would be an optimized, and they can do the maintenance before it can be planned before breakdown also. So this application was developed for the airline for this particular purpose of maintenance. Thanks for watching it.